want to talk about sampling proportions. The notes were a little unclear as to what the heck is going on with sampling proportions. Why are we able to, at all, treat a sampling distribution for proportions like it's normal? So with this video, I'd like to sort of show you an example of what's going on, similar to the one that we had with sampling means, just so you can get a better understanding of what exactly is happening. So here we have a candy machine with an infinite amount of Reese's Pieces, we'll say. And it seems that half of the Reese's Pieces are orange. So the notion that half the Reese's Pieces are orange isn't a distribution, right? It's not something that we can graph it. It's like it would just be a bar graph where one bar for orange goes up to half, and then the other bar for the other candies goes up to whatever, the half, or if you split them up, then like whatever, right? So it's sort of like a binary situation. Either it's, orange, or it's not. There's not really an in-between. It's a binary choice. So the thing is, we know that because of that, if we take any one candy out, the probability of that one candy being orange is 50%, right? So if I just take one at a time and I keep track of the orange candies, I see that, half of them are orange, half of them are not. Okay, that's not very interesting. What happens if we take maybe 6 candies at a time, right? So half of them are orange. We should expect that, half of them in the 6 would also be orange. The thing is, we also know that because of the way things work, probability suggests that not all of the time will we get 3 orange candies out of 6. We know that sometimes we'll get less, sometimes we'll get more. But by how much is the question? Well, if we're only talking about one sample, then we could treat it like a binomial, but that's not exactly what's going on here, right? We've done binomial distributions. We know how those work. Instead, let's just see what happens when we do it. So 6 at a time. First time out, already we didn't have 3. Let's just keep going and see what happens. Okay, so I've taken 100 samples. Most of the time, for this round, out of the 6 candies, 4 of them were orange. That's a little weird, but we know it's bound to happen every now and then. Let's keep going, but we'll up the sample size to 10 at a time. I'm sorry, we're upping the samples to 10 at a time, not the sample size. Sample size is still 6. So 10 different handfuls of 6 candy. All right, so we've taken just over 1,000 samples of size 6, so just over 6,000 pieces of candy. And we see that, half of the time, 3 out of the 6 were orange. So that's kind of nice. And we see, it kind of looks a little bit normally distributed. That's all well and good. So then that begs the question, can we treat something as normally distributed if the sample size is small, like in this case, 6? And the answer is no. In this one specific instance, you might get away with it, but we know that, we can show that based on what the probability would be, the sample size is going to matter. We also saw that in this example, it took us getting 1,000 different samples before we got something that looked even close to normal. This is still, it works, but it's not that great. The sample size is just too small. So let's change this to something, let's say 0.75. Let's say 3/4 of the candies now are orange. And we're going to take, one at a time of handfuls of 6 candies. What's going to happen here? Well, let's find out. All right, so we see that it's clearly not normally distributed. The last one wasn't normally distributed yet either, but now the peak is over here at 5, right? So that's even further away than it was before. So let's do what we did last time. Let's up the sample size to 10, and let's see what happens if we take just a whole bunch of samples. All right, so it's starting to become a little bit obvious. We see that while, yes, it's curving a bit, we see that it's very much a skewed distribution. The majority of the time, we have 5 out of 6 candies being orange. The second most, we have 4. This makes sense because 75% of the candies being orange would be halfway between 4 and 5. However, this still isn't something that's normally distributed. It's very much skewed to the left. It peaks way over here on the right, and it skews to the left. So, okay, does that mean we can only do, treat something as normally distributed if the probability is half? Well, no, it doesn't. The important thing here is that the sample is too small, right? We don't have enough room for this to curve off. The rule that we use for proportions, and it's mentioned in the notes, is that there has to be enough room in your sample for you to expect at least 10 successes and 10 failures. And successes and failures are defined the same way they were when we were talking about binomials, because these are largely the same, with some slight differences. So if 75% of the candies are orange, that means in order for us to have 10 successes and 10 failures, we have to increase our sample size. Successes means there has to be orange candies, at least 10 orange candies, and at least 10 failures means there has to be at least 10 non-orange candies. So if 75% of them are orange, in order for us to get at least 10 orange candies and 10 non-orange candies, our sample size has to be 40. If we increase our sample size to 40, then if 75% of them are orange, then that would be 30. And then if 25% of them aren't orange, that would be 10. So we have at least 10 successes and 10 failures. If we run this same thing again, just like we did the last time, we'll see something slightly different. Okay, so we're only at 100 candies this time, and we already see it starting to take more of a normal distribution type shape. It's clearly peaking here in the middle, and it's clearly tailing off relatively balanced on both sides. Let's do what we did last time and increase this to something a little bit more substantial and just see what we get. All right, so we've taken 1,000 samples of size 40, where 75% of the candies in the population were orange, 25% of them weren't, and yeah, so big handfuls of candy. We see that again, this is something that we can start to treat like a normal distribution. Now keep in mind, a true sampling distribution is the notion that you've taken all possible combinations of that sample size and made a graph out of what, in this case, proportion of them fit whatever criteria you're talking about. So most of the time we had 30 out of the 40 be orange, and then in either direction it tails off, sometimes a little more slowly than others. But again, in order for this to be perfect, we would have to get a lot more samples. When we superimpose this over a normal approximation, we see that yes, this is getting pretty close to normal. We can keep this up and take a lot of samples, and the more we take, the closer it gets to something that's normally distributed. So that's good. Now, why is that a big deal? Well, the idea is that we want to be able to use the normal distribution that we've been using, the same tools that we've been using, to make predictions about the probabilities that we get a certain proportion in any given circumstance. And of course, this doesn't just apply to candies. You can talk about any population having a certain characteristic. If you know from the overall population what proportion of them or what percent of them have a certain trait, you can predict the probability that you'll have less than a certain amount or more than a certain amount in any given population. Now, of course, the true sampling distribution that you're using isn't something that really exists, because getting all possible combinations of your sample size from a real population isn't something that's practically done. But because we see that if we continue to do this, it becomes normally distributed, we can treat it like a normal distribution. We know that it's going to be a normal distribution if we went ahead and did it, because it approaches normal the further along we go. Now, what is significant about the 0.75? Well, if you see 30 out of 40 of them in this distribution, that is the center, right? So the mean of this distribution is equal to the proportion of the population that fit the criteria you were talking about. 0.75 is the center of this distribution. If we're going to use a sampling distribution to find the probabilities, that sampling distribution will be normally distributed and centered around 0.75, meaning when we're going about doing our calculations, we know the mean is just going to be whatever proportion we got from the problem. Now the standard deviation we talked about, it's very similar to what it was when it was a binomial distribution. However, instead of having the square root of n times p times 1 minus p, the n will be on the bottom of a fraction. So it will be the square root of p times 1 minus p over n. And that's really the only difference. So that's how you calculate that standard deviation. We treat it very similarly to how we treated binomials, but the variance is a little bit different because it gets smaller the larger your sample size. This one stretches from 0.53 to approximately 0.97, but if I increase the number of candies in any given sample to 400 instead of 40, I see that the range of this shrinks from that to about 0.66 to 0.82. So the standard deviation decreased when we increased the sample size. So that's why the n goes on the bottom of the fraction instead of on the top. Anyway, I hope this was helpful. This is the reasoning why we're able to use a normal approximation when we're talking about something like a proportion of a population.